Section: Contents. In this section, we discuss the evolution of foundation models into multimodal large language models, LLMs, that can handle various data types like text, images, and speech within a single framework. Recent models, such as Chameleon, show that early fusion, mixed-modal models can create different media types in one architecture. While these models are promising for applications like content creation and cross-modal translation, they face significant computational challenges because they need to learn from multiple data types at once. Training these early fusion multimodal LLMs requires much larger datasets and more computational power than single-modality models. For instance, Chameleon is trained on 9.2 trillion tokens, including image tokens, while Llama 2 is trained on 2 trillion tokens focused on text. Each data type brings its own optimization challenges, which we must tackle together in a unified model. We observe that different modalities often have conflicting training dynamics, complicating the optimization process and increasing computational demands. To tackle these challenges, we consider model sparsity, such as the mixture of experts (MO) approach, which allows us to activate only a portion of the model components for each input, thus reducing the computational load. In MO, a learned router activates one of several networks in each transformer layer, enabling different experts to focus on various data aspects. However, MO also presents challenges, such as imbalanced expert usage and complex training dynamics that can become unstable as model sizes grow. In multimodal contexts, previous research has introduced modality-aware sparsity in MO layers or fine-tuned specific modules on LLM backbones. These methods have shown that simple, rule-based routing by modality can outperform the learned routing typically used in MO, likely due to more stable training dynamics. Building on these insights, we propose mixture of transformers, MO, a sparse multimodal transformer architecture that applies modality-aware sparsity to all non-embedding transformer parameters. Unlike previous methods, MO implements this sparsity throughout the entire transformer, not just in specific layers. MO processes an interleaved sequence of different modalities, like text, image, and speech, and applies unique parameters to each token, maintaining the same computational structure and overall complexity as a dense transformer. We evaluated MO by pre-training 13 models, including 3 7 billion parameter models, across various multimodal scenarios. This allowed us to test MO's performance under different training objectives and modalities. For example, in the Chameleon setting, our 7 billion MO model matched the performance of a dense baseline while using only about 56% of the computational resources. When we added speech as a third modality, MO maintained similar performance across all modalities while requiring even fewer resources for speech. In another scenario, where we used different training objectives for text and images, our 760 million MO model outperformed a larger dense model across several metrics while using half the computational resources. To further assess MO, we conducted additional experiments to evaluate its efficiency and effectiveness compared to other sparse architectures. Our findings showed that MO significantly reduces training time, achieving comparable performance to a dense model in less time. We also compared MO to a mixture of experts model with more sparse parameters, finding that MO consistently outperformed it, especially in non-text modalities. Lastly, we explored a hybrid approach that combines sparse transformers within the MO framework, using the MO architecture for text tasks while keeping the original MO design for image tasks. Preliminary results indicate that this combination can enhance text performance without sacrificing image quality. Section Summary. In this section, we discuss the advancements in multimodal large language models, LLMs, like Chameleon, which integrate various data types but face significant computational challenges. We propose a new architecture, mixture of transformers, MO, that employs modality-aware sparsity across the entire transformer to enhance efficiency and performance, demonstrating substantial reductions in computational load while maintaining competitive results across multiple modalities. Section: Background. Foundation models for multimodal generation. In this section, we discuss the background of foundation models for multimodal generation. Recent developments in large language models have moved beyond just text, allowing us to tokenize non-text data like images and speech into sequences of discrete tokens. We apply auto-regressive sequence modeling to these data types, similar to how we handle text. For instance, Chameleon tokenizes images into 1024 discrete tokens using a pre-trained image tokenizer, enabling unified training across text and images. Similar techniques have also been used for speech. We also explore alternative methods, such as transfusion, which utilize continuous image tokens and a diffusion-based training objective to enhance the generation of continuous data like images. To understand how multimodal foundation models represent information internally, we analyzed their feature space. Our findings show that different modalities, text, speech, and image, cluster together across various layers. Using principal component analysis, we identified distinct areas for each modality in the feature space, even though all inputs are processed uniformly as discrete tokens without specific prior knowledge for each modality. This natural clustering indicates that there are inherent differences in how each modality is processed, which informs our approach. Next, we introduce the mixture of transformers, MO, architecture, which is designed to speed up multimodal pre-training while lowering computational costs. MO builds on the standard transformer architecture by adding modality-specific weights for all non-embedding parameters, such as feed-forward networks and attention matrices. This allows us to process different modalities more effectively while still learning how they interact with each other. In our MO model, we separate the parameters by modality but keep a global self-attention mechanism that works across all modalities, capturing their relationships. The computation process starts by grouping input tokens by modality, applying modality-specific projections for attention, and then performing global self-attention. After that, we apply modality-specific output projections, layer normalization, and feed-forward networks. We evaluated the MO architecture in 3 multimodal experimental settings, each with increasingly complex training objectives and modalities. For each setting, we compared MO to 2 baseline models, a dense transformer and a mixture of experts model with 4 experts. All models were built on the dense model and had the same computational load for training and testing, allowing us to compare efficiency and performance directly. In the first setting, we used autoregressive objectives with both text and image modalities. Images were represented as 1024 discrete tokens through a pre-trained model. We assessed MO's performance against the baselines using various training and evaluation metrics. In the second setting, we extended the previous experiment by adding speech as a third modality, also represented by discrete tokens from a pre-trained speech tokenizer. This allowed us to evaluate MO's efficiency and performance with an additional modality. In the third setting, we explored multi-objective training, using autoregressive objectives for text and diffusion-based objectives for images. This highlighted MO's ability to manage different training objectives for each modality, potentially enhancing image generation quality while maintaining text generation capabilities. The following sections will provide detailed results for each experimental setting, including comprehensive comparisons of MO against the baselines across various evaluation metrics. We will also present an ablation study that examines how modality-specific decoupling affects model performance in different transformer components. Finally, we will evaluate the MO architecture in the Chameleon setting, focusing on autoregressive objectives for text and image generation. Section Summary. In this section, we discuss the development of the mixture of transformers, MO, architecture, which enhances multimodal pre-training by utilizing modality-specific parameters while maintaining global self-attention for cross-modal interactions. We evaluate MO's performance across various multimodal settings, demonstrating its efficiency and effectiveness in handling different modalities and training objectives. Section: Data and Pre-Processing. In this section, we describe our data and pre-processing methods. We utilized the same mixed modal training data and text and image tokenizers as previous work. Our training data consisted of roughly equal amounts of text and image tokens. We assessed the performance of our 7B model by looking at validation losses on separate sets from the MS COCO, Flickr 30K, and Shutterstock datasets. Specifically, for MS COCO and Flickr 30K, we used the Carpathy test splits and reported the conditional perplexity for both text-to-image and image-to-text tasks. Regarding model hyperparameters, we evaluated the mixture of transformers, MO, across various model sizes, ranging from 37 million to 7 billion parameters, and compared it to dense transformer and Mo4X baselines. All models were pre-trained from scratch with controlled computational resources for a fair comparison. We progressively scaled model architectures, increasing hidden dimensions from 256 to 4096 and layer counts from 4 to 32. The number of attention heads increased from 8 to 32, while the sequence length remained constant at 4096 tokens. As the model size grew, we reduced the batch sizes per GPU from 12 to 2 and increased the number of GPUs from 32 to 384. We set the training steps at 160,000 for smaller models and 120,000 for larger ones, processing a total of 0.168 to 0.377 trillion tokens, with most configurations around 0.252 trillion tokens. This allowed us to analyze Mo's performance across different model sizes and computational resources. For our Mo4X baselines, we implemented expert choice (EC) routing, which balances the load during training by having each expert select the top inputs based on routing weights. However, EC cannot be directly used for auto-regressive generation due to the causal dependency of tokens. Previous studies have suggested various adjustments for maintaining generation causality in Mo models trained with EC routing. We evaluated all models using the same EC routing during training, focusing on validation perplexity. This method ensured a consistent computational setting with the dense baseline but introduced two potential issues. It might overestimate Mo4X's performance by allowing access to future tokens and could underestimate it if the evaluation data distribution differed significantly from the training data. We recognize these limitations and discuss the results in relation to Mo4X in each experiment for a clearer understanding. In terms of accelerated pre-training at the 7B scale, the Mo architecture showed significant speed improvements. Mo reached the dense model's final loss in half the time, achieving equivalent performance at just 60,000 steps. We quantified this acceleration through step matching analysis, which illustrated that Mo consistently required only 45.5% of the dense model's training steps to reach similar pre-training loss. Modality-specific analysis indicated that Mo was particularly effective in the image modality, needing only 34.8% of the dense model's training steps to match final loss. For text, both Mo and Mo4X outperformed the dense model, with Mo showing comparable or slightly better results. Validation loss results further supported these findings, demonstrating that Mo achieved validation losses comparable to or lower than the dense model's final validation loss with only 55.8% of the training steps, indicating significant computational savings. We also extended our analysis of Mo to 5 additional model scales within the chameleon setting. Mo consistently provided significant speedups in the image modality across all scales, outperforming both the dense model and Mo4X. We noted that Mo4X showed diminishing returns as model size increased, with its advantages in the image modality decreasing at the 7B scale. In contrast, Mo maintained its performance across all scales. For the text modality, both Mo and Mo4X outperformed the dense model, with Mo showing comparable or slightly better gains. Validation loss results across these scales remained consistent with the training loss trends, demonstrating that Mo's advantages extend across various model sizes, highlighting its efficiency for large-scale multimodal generative tasks. Section Summary. In this section, we describe our use of mixed modal training data and tokenizers, evaluating the 7B model's performance on various datasets while comparing different model scales and architectures. We highlight the mixture of transformers, Mo, architecture's significant pre-training acceleration, particularly in the image modality, and its consistent performance advantages across multiple model sizes compared to dense models and Mo4X baselines. Section: Extending to a third modality, chameleon text plus image plus speech results. In this section, we evaluated the performance of Mo in a multimodal context by adding speech as a third modality alongside text and images. Our experiments focused on the 7B model and smaller versions, comparing Mo with dense and Mo4X models that were pre-trained from scratch while controlling for computational resources. For our experiment setup, we used the training dataset from Spirit LM as our speech dataset. This dataset included both speech-only samples and combined speech-text data. We converted speech input into discrete tokens using our in-house tokenizer, which creates semantic tokens with a vocabulary of 500, where each token represents 40 milliseconds of audio. We combined the speech dataset with the chameleon text and image dataset at a ratio of 1:6, maintaining the same mix ratio within each dataset. This setup allowed us to assess Mo's ability to manage complex multimodal inputs, addressing the challenges of speech processing while ensuring efficiency across all modalities. We followed the evaluation methods from the chameleon setting and reported validation losses for the speech modality on separate datasets. When integrating speech at the 7B scale, we found that the Mo model showed significant acceleration in pre-training. Specifically, Mo achieved comparable speech pre-training loss to the dense model in just about 23% of the training steps, indicating high computational efficiency. It consistently outperformed the baseline models in validation loss on the speech datasets. Additionally, Mo maintained its efficiency in image and text modalities, achieving similar or lower validation losses than the dense model at only 56% of the training steps, showcasing its strong performance in multimodal settings. We also extended our evaluation to smaller model sizes, such as 443M, 880M, and 1.5B, in the chameleon text plus image plus speech setting. Mo consistently demonstrated significant acceleration across all modalities, especially in speech processing, requiring only 15% to 34% of the dense model's training steps to match speech training loss. The Mo4X model performed poorly in speech tasks, showing some improvements in training loss but unstable validation results. In contrast, Mo outperformed both dense and Mo4X models across all scales in speech tasks, highlighting its adaptability and reliability in generative AI applications. In the transfusion setting, we introduced a unified framework that allows a single transformer model to handle both discrete text and continuous image modalities. The innovation here is the use of separate loss functions for each modality, language modeling loss for text and diffusion loss for images, while sharing data and parameters within one architecture. We evaluated Mo's performance under this multi-objective training setup, where text is trained with autoregressive objectives and images with diffusion-based objectives, all pre-trained from scratch under controlled conditions. For data and pre-processing, we used the Llama 2 tokenizer and a corpus containing 2 trillion tokens from various domains for text. Images were encoded into latent patches using a variational autoencoder, with each patch representing a continuous vector. We utilized a collection of 380 million licensed Shutterstock images and captions, resizing each image to 142 by 142 pixels. For multimodal examples, we enclosed each image sequence with special tokens before integrating it into the text sequence, resulting in a single sequence that includes both text tokens and image patches. We randomly ordered the images and captions, placing the caption first half of the time, and in most experiments, we sampled 0.5 trillion tokens from both modalities at a 1:1 ratio. Section Summary. In this section, we evaluated Mo's performance by integrating speech as a third modality alongside text and images, demonstrating significant pre-training acceleration and efficiency across all modalities, particularly in speech processing. Our findings indicate that Mo consistently outperformed dense and Mo4X models in both training and validation metrics, showcasing its scalability and reliability in multimodal generative AI applications. Section: Model Hyperparameters. In this section, we explore the model hyperparameters and scaling trends by training models of various sizes: 0.16 billion, 0.76 billion, 1.4 billion, and 7 billion parameters. We present the model architecture and training configurations in a table. We keep the UNet patch encoding parameters constant at an additional 0.27 billion parameters for all configurations. All model parameters are initialized randomly and optimized using the AtomW optimizer with specific settings, including a learning rate of 3 × 10⁻⁻⁴, which is warmed up for 4,000 steps and then decays to 1.5 × 10⁻⁵ using a cosine scheduler. We train on sequences of 4,096 tokens in batches totaling 2 million tokens for 250,000 steps, reaching a total of 0.5 trillion tokens. We apply weight decay of 0.1 and gradient normalization of 1.0 for regularization. During inference, we perform 250 diffusion steps. For evaluation, we assess the model's performance on standard unimodal and cross-modal benchmarks. For text-to-text tasks, we calculate perplexity on 20 million held-out tokens from Wikipedia and the C4 corpus. For text-to-image tasks, we report the diffusion validation loss based on the South Dakota 3 model using held-out conceptual 12 million data. We also utilize the MS-COCO benchmark, generating images from 30,000 randomly selected prompts from the validation set. We evaluate the photorealism of these images using the zero-shot Frechet inception distance, FID, and their alignment with prompts using the clip score. Additionally, we measure the model's ability to generate image captions by reporting CIDR scores on the Karpathy test split of MS-COCO. In the transfusion setting, we find that the mixture of transformers, MO, architecture significantly speeds up pre-training for the image modality at the 7 billion parameter scale. Compared to dense and MO4X models, MO achieves similar image pre-training loss to the dense model in only 30% of the training steps. MO's efficiency is further demonstrated by better diffusion validation loss, higher COCO 30K clip scores, and lower FID scores. When comparing our 7 billion model to external models, we find that it achieves a COCO 30K FID score of 8.14 at a guidance level of 1.6, while a dense model trained on 1 trillion tokens scores 9.22 under the same conditions, highlighting MO's efficiency. In image understanding tasks, MO shows more than a threefold speedup compared to the dense model, achieving a final score of 40.6 versus 31.5. We do not include MO4X caption performance due to potential information leakage. These results extend our findings from the Chameleon 7 billion setting, where MO matched the dense baseline's image pre-training loss using only 34.8% of the floating point operations. The improvement in text performance for MO in the transfusion setting was less significant than in the Chameleon setting, where MO required only 54.6% to 66.2% of the training steps to match the dense model's text training loss. In transfusion, the text performance improvement was minimal, likely due to the separate training objectives for image and text modalities, which led to nearly optimal text performance. The decoupling of training objectives in the dense model may provide benefits similar to MO's decoupling of modality weights. At smaller scales, MO shows notable performance gains, especially in the image modality. A 760 million parameter MO model, operating at half the floating point operations of a 1.4 billion parameter dense baseline, consistently outperforms its larger counterpart across various metrics. Image quality improves, as indicated by clip and FID scores. The image captioning capability, measured by CIDR score, also shows improvement. When comparing models with an 8-fold difference in size, the 163 million MO achieves comparable image modality training loss. Although the 163 million MO slightly lags behind the 1.4 billion dense model in evaluation metrics, the significant reduction in both training and inference compute underscores MO's strength in the image modality. Section Summary. In this section, we detail our training of models with varying sizes, 0.16b to 7b parameters, using fixed U-net patch encoding and specific optimization techniques, achieving significant efficiency with a mixture of transformers, MO, architecture, which accelerates image pre-training and outperforms dense models in various benchmarks. We also observe that while MO shows substantial gains in image tasks, its impact on text performance is less pronounced due to the separate training objectives in the transfusion setting. Section: Scalability across model sizes. In this section, we demonstrate that MO consistently outperformed baseline models in image tasks across various sizes, including 163 million, 760 million, and 1.4 billion parameters. We observed significant improvements in FID scores for MO compared to dense models, with scores of 21.58 versus 27.42 for 163 million, 15.75 versus 25.58 for 760 million, and 15.85 versus 19.32 for 1.4 billion. Additionally, CLIP scores also showed consistent enhancements with MO, 0.195 versus 0.185 for 163 million, 0.214 versus 0.202 for 760 million, and 0.217 versus 0.206 for 1.4 billion. In text tasks, MO matched dense models in training and validation loss on text-only datasets but excelled in captioning tasks, achieving higher CIDR scores, 0.232 versus 0.147 for 163 million, 0.320 versus 0.251 for 760 million, and 0.335 versus 0.286 for 1.4 billion. As noted in our results, MO showed limited improvement in text performance across scales. For fine-tuning, we followed the original transfusion setup and fine-tuned the 7 billion parameter MO and dense models on an internal visually appealing dataset and image editing tasks. The fine-tuned models were able to generate text, detailed hand features, fictional images, and photorealistic images. After fine-tuning, MO exhibited better quality and higher fidelity compared to the fine-tuned dense models, indicating that the performance advantage of MO is preserved post-fine-tuning. Importantly, we trained on only 0.5 trillion tokens, which is much less than other leading image generation models, suggesting that our model is not yet saturated even at 2 trillion tokens. We plan to scale up our model and train with more data in future work. We also fine-tuned the 7 billion MO on 8,000 image editing data, which allowed it to generate images based on other images following text instructions. We conducted ablation experiments to assess the impact of modality untying in different transformer components. We controlled the architectures to match the dense architecture in terms of computational load. We compared 4 model variations: the dense baseline, a model with modality untying only in the feed-forward module, a model with untying in both the feed-forward module and the attention weight matrices, and the full modality untied MO model. Our findings showed that untying in the feed-forward module alone significantly enhanced performance, especially for image tasks. Further untying the attention weight matrices led to additional performance improvements. On the held-out set, this resulted in about 33.3% savings in computational load for image tasks and 10% for text tasks compared to just untying in the feed-forward module. We believe this is due to the feed-forward module's larger share of computational load in our context and its role as a memory component in transformers. We also found that untying layer norm parameters had a minimal effect on evaluation performance. To evaluate the effectiveness of MO's modality-specific architecture, we performed a Leave One Modality Out (LU) analysis using the Chameleon framework, which includes text, image, and speech. This analysis aimed to measure the advantages of separating modalities into distinct transformer towers, as done in MO, versus combining them in a single tower. We tested 3 LU variants where 2 modalities shared the same transformer while one was isolated. A dense transformer architecture with all modalities in one tower served as our baseline. All models were designed to have equivalent computational loads for a fair comparison. Section Summary. In this section, we demonstrate that Mo consistently outperforms dense models across various scales in image tasks, showing significant improvements in FID and clip scores, while also achieving better generalization in text captioning tasks. Additionally, our fine-tuning experiments reveal that Mo maintains superior quality and faithfulness in image generation, and our ablation studies highlight the benefits of modality untying in enhancing performance and reducing computational costs. Section: Results. In this section, we present our findings from the Leave One Modality Out (LU) analysis, which highlighted the benefits of keeping modalities separate in the Mo architecture. We observed that combining modalities generally led to worse performance, as indicated by increased training and validation losses. The LU text configuration had the lowest loss for text, while LU image and LU speech showed the best results for their respective modalities. These findings emphasize the need for modality-specific parameter allocation in Mo. We also noticed that the effects of combining modalities varied. In LU speech, separating speech maintained Mo's advantages for that modality but hindered improvements in image and text. Similarly, LU image preserved most of Mo's gains in image performance, while merging text and speech caused declines in both. In LU text, combining speech with image led to a drop in speech performance, although the image modality largely retained its improvements from Mo. This suggests that different modalities may compete with each other in non-reciprocal ways. By using separate transformer towers for each modality, Mo can better optimize for their unique characteristics, leading to improved overall performance. Next, we explored the combination of Mo and Mo4X in the chameleon setting. We modified the Mo architecture by integrating Mo4X into the text transformer tower, replacing the text feed-forward network with the Mo4X mechanism, while keeping the image transformer unchanged. Our goal was to see if this integration could enhance Mo's performance in multimodal tasks. The results showed that this combination significantly sped up the reduction of text training loss compared to the dense model, Mo4X, and Mo alone. The combined model maintained or improved upon Mo's performance in both text and image tasks, with the best text validation performance across multiple datasets. Importantly, the image performance remained comparable to Mo, indicating that adding Mo4X did not compromise Mo's efficiency in image generation. We then extended our experiment to the transfusion setting, where we applied different objectives to each modality: autoregressive for text and diffusion-based for images. We again replaced the text transformer's feed-forward layer with a 4-expert Mo layer, while keeping the image transformer the same. This approach continued to accelerate text training loss reduction compared to the dense model and Mo alone. The combined model preserved Mo's advantages in image performance, showing similar training loss and speedup. Our validation results confirmed the effectiveness of this approach, with Mo plus text Mo4X achieving the best text performance while maintaining Mo's efficiency in image tasks. Although Mo4X showed lower text training loss than the dense model, it did not significantly improve text validation losses, reinforcing the effectiveness of the Mo approach. Overall, our preliminary results in both the chameleon and transfusion settings demonstrate the potential of combining Mo and Mo4X. The integration of Mo4X into the text modality enhances text performance, while Mo continues to excel in image generation. We plan to further investigate the scalability and generalizability of this approach across additional tasks and modalities. Section Summary. In this section, we demonstrate that separating modalities in the Mo architecture enhances performance, as evidenced by lower training losses for isolated modalities compared to combined ones. Additionally, we explore integrating Mo4X into the text transformer of Mo, which significantly improves text performance without compromising image generation efficiency, suggesting a promising direction for multimodal model enhancement. Section: ML Systems Aspects of Mixture of Transformers. In this section, we highlight some system properties of mixture of transformers, Mo, and show how these properties translate into real-world advantages during training. First, we discuss throughput scaling properties. The modality-based scaling method used by Mo results in a lower ratio of parameters to floating point operations, PPF. This ratio is important for training speed in large-scale cloud environments, where communication overhead can slow down distributed learning. Recently, compute power has grown faster than network bandwidth, making smaller models more efficient for training. We compare the number of parameters added to each transformer layer when using 188 experts in a mixture of experts, Mo, versus untying 189 modalities in Mo. In a typical transformer setup, we find that Mo generally has a lower PPF ratio, which can be beneficial in practical scenarios. Next, we look at compute efficiency. Both Mo and Mo have extra overheads when routing tokens to the right parameters. Mo faces challenges due to operations like selecting the top experts and managing token outputs, which can create latency. On the other hand, Mo's overhead mainly comes from two areas: the need for CPU-GPU synchronization when grouping tokens and the sequential processing of modalities, which can lead to inefficient GPU usage. However, we can reduce these overheads through careful engineering, such as caching sequence indices and using specialized matrix multiplication techniques. We plan to explore these improvements in future work. For our empirical analysis, we conducted experiments on AWS using powerful GPU instances. We examined how Mo scales with the number of GPUs. As we increased the GPU count, we also increased the global batch size and total training tokens while keeping the training steps constant. Our results show that Mo's performance improves significantly with more GPUs. For instance, the percentage of training steps needed for Mo to match the dense model's performance dropped from 42.1% with 16 GPUs to 21.6% with 256 GPUs for image validation loss. For text, it decreased from 75.7% to 50.9%. This indicates that Mo becomes more efficient as we add more compute resources. Finally, we examined the wall clock time performance of Mo. This analysis is important for understanding how Mo performs in real-world training scenarios, where we aim to achieve the best model quality within a set GPU training time. Our results, obtained from a specific AWS setup, suggest that the performance of Mo, and dense models may vary across different environments. However, we believe our findings are relevant for typical cloud computing deployments. We found that Mo significantly outperforms both dense models and Mo in terms of training time on 256 GPUs. Specifically, Mo matches the dense model's image training loss in just 47.2% of the total GPU training time and continues to improve. For text, Mo requires 75.6% of the dense model's time to achieve similar performance. In contrast, Mo shows no speed advantage for text and even slows down for images compared to the dense model. Our results are consistent across evaluation losses on the dataset. Section Summary. In this section, we highlight the system properties of mixture of transformers, Mo, and their real-world benefits, demonstrating that Mo maintains a lower parameter-to-flops ratio, which enhances training throughput in large-scale environments. Our empirical analysis shows that Mo's performance improves significantly with increased GPU count, achieving faster training times compared to dense models in Mo, particularly in both image and text modalities. Section: Foundation Models for Multi-Modal Generation. In this section, we discuss the advancements in large language models, LLMs, that have expanded into multimodal applications. Initially, early multimodal LLMs concentrated on understanding rather than generating content, using techniques that combined separately encoded images and text. While these models were easy to train, they did not support multimodal generation. To facilitate this, a crucial method involves breaking down non-text formats into distinct sequences. For example, models like Chameleon tokenize images into 1024 separate tokens using pre-trained models, training on combined sequences of text and image tokens. Similar methods have also been applied to speech. Recent models, such as transfusion, have looked into using continuous image tokens and specific loss functions to improve visual generation quality. Our proposed mixture of transformers method aligns with these strategies and can seamlessly replace dense transformer architectures. We show significant improvements in various multimodal scenarios, including those involving chameleon and transfusion. Next, we explore sparse architectures, particularly the mixture of experts, MO, which have shown potential in text-based models by allowing dynamic selection of parameters for each input. Recent adaptations of MO for multimodal tasks have tackled the challenges arising from the differences in feature spaces between modalities. These adaptations suggest that allocating parameters specific to each modality can enhance performance by addressing the unique characteristics of different data types. In contrast to previous works, we introduce the mixture of transformers, MO, framework, which expands on the MO concept by separating all non-embedding parameters within the transformer structure. MO consistently outperformed MO in multimodal pre-training when the total number of parameters was controlled and showed compatibility with MO 4x. While recent studies have extended MO to attention mechanisms, our approach stands out in several ways. Unlike COG-VLM, which is limited to generating text, MO can generate both images and text. At the same time, Playground V3 integrates a specific image transformer with a text backbone, achieving top performance in generating text and images. During its training, the text LLM remains unchanged while only the image transformer is updated. While both COG-VLM and PGV3 build on pre-trained LLMs for multimodal training, we position MO as a versatile sparse architecture that can be trained from the ground up. MO also separates every non-embedding parameter across transformer layers, including layer normalization, unlike previous methods that share layer normalization parameters. Our results highlight MO as a flexible and scalable option for multimodal pre-training, showing its potential to enhance MO-based architectures and paving the way for more efficient large-scale multimodal models.